Hi everyone, I'm Sean Barker. I'll be presenting an empirical study of memory sharing in virtual machines. This is joint work with Timothy Wood, Prashant Shenoy, and Ramesh Shataraman at the University of Massachusetts Amherst and the George Washington University. So how do we normally use virtualization? Well, one way we often use it is in data centers to improve resource utilization. So what virtualization does for us is it allows us to flexibly map the resources we have available to the users we want to service. So practically what this means is that we can basically have more logical servers and service more applications using a smaller total hardware footprint. Now, of course, we'd like to maximize the benefits we get from doing this. And in practice, this means we want to efficiently share resources between our VMs. So one way to think of this is a question of virtual machine placement. So we might have 2 physical servers and 4 virtual machines, and we'd like to place those VMs so that we are optimally sharing resources between them. Now, one way we have to actually do this resource sharing is what we call content-based page sharing. So the idea here is that we want to eliminate identical pages of memory across multiple VMs. So let's look at a simple example of how this might work. So we have some physical memory, and we have, in this example, we have 2 virtual machines, each with 3 pages, and then the color and label here indicates what the content of a given page is. So the hypervisor is going to take those virtual pages and map them into physical memory. In content-based page sharing, what's then going to happen is the hypervisor is going to detect duplicates. In this case, there are 2 of them, A and B. And we're going to replace those with copy-on-write references to the original copies. And so what we gain from doing this is those copies that we have, those duplicates we've detected, are then freed up, and we've reduced the total amount of memory we're using. So there's been a lot of prior work in actually doing this page sharing. The oldest commercial support comes from VMware. They had a paper in 2002, and their approach is basically based around periodically scanning memory to detect duplicates and reported, in some cases, upwards of 30% memory savings. More recently, in 2008, Difference Engine looked at sharing memory on sort of a sub-page granularity and patching pages that were very similar to each other. They reported, in some cases, upwards of 60% memory savings. And in 2009, Satori focused on looking at short-lived pages and reported that they could capture over 90% of possible sharing. So this all sounds really great for page sharing, but there are some sort of important open questions that haven't received a whole lot of attention, and I'm going to highlight a few of those. One of them sort of just pertains to real-world machines. That is, sort of what kind of levels of sharing should we expect in sort of a typical real-world machines, and how might this compare to what we've seen in laboratory studies? Another important question is about sort of the important factors that affect sharing potential. We can think of a number of different factors, but it's sort of important to consider, well, how important relatively are these various factors? Another question is sort of how will emerging and evolving technology actually impact our ability to share. So for example, we could consider OS technologies are changing. We can also consider things like new emerging paradigms, things like large-scale VDI farms or LAMP clusters, these types of things. So broadly speaking, in this work, our goal is to provide some practical insights into these questions through a study of a lot of memory data. So I've given some background and motivation in this work. Next, I'm going to talk about the data we're looking at and also the types of sharing we're looking at. Then I'll present a study we've conducted on sharing potential in some real-world memory traces, and then sort of a study of some specific factors impacting sharing, and then I'll conclude. So we have 2 main bodies of data that we're looking at. The first is a set of real-world memory traces. So we have memory data from about 50 real machines, both a mix of servers and desktops. And these machines are running completely uncontrolled user workloads. These are departmental machines and user desktops and servers and so forth. And on these machines, we've been collecting memory snapshots every 30 minutes. So these are raw user workloads. We don't know anything about what's actually going on in them. But in addition to this, we'd also like to be able to look at specific scenarios. So in order to do that, we also use some supplementary traces from virtual machines that we set up ourselves. So this allows us to sort of, vary exactly what's going on in those VMs. We can vary, what the operating system is, what the versions are, the architecture of the OS, so on and so forth. We can also look at a variety of different, workload setups. In particular, we're sort of looking at 3 basic application setups. One where there's sort of no workload, we just have the VM. One in which we're sort of running a typical LAMP stack, and then one which is sort of a typical desktop deployment where we're running some, typical desktop applications. Within our data, we're also looking at sort of 2 different types of sharing. The first type is what we call self-sharing, and this is basically sharing within individual VMs. And a very easy example of this is multiple zero pages. So an example of what this might look like, in this example we have 3 machines. Each of those machines has 3 copies of an identical page. So within each of these machines, we can eliminate 2 of those copies. And so across these 3 machines, we are achieving savings of 6 pages. But we can also consider inter-VM sharing, and this is sort of what we more typically think of when we say, page sharing. And this is sharing across multiple VMs due to things such as, shared operating system state. And this is an example of what that might look like. In this example, we have, a single shared machine, 3 virtual machines, and each of those virtual machines has 3 unique pages, but the hypervisor can share 2 of those copies of each page. And here we're achieving, again, 6 pages of sharing. But in the top, that's all self-sharing. In the bottom, that's all inter-VM sharing. So we sort of are interested in both the amount of self-sharing and the amount of inter-VM sharing that we're seeing. So next, I'll present a study of our real-world memory data. So first, let's look at the amount of self-sharing we see in some of our traces. So this graph here shows a sampling of 7 of our machines along the x-axis. Along the y-axis, we have the total percentage of self-sharing that's possible over a week-long period. We have the average, the maximum, and the minimum we observed at any snapshot during that week-long period. So what are we seeing here? Well, one thing we're seeing is that there's sort of an average level of self-sharing of about 14% across these machines. Now, this is, not huge, but it's certainly significant. And it's also important to consider that this is actually entirely excluding zero pages. In general, we're not too interested in looking at zero pages because most zero pages tend to be pretty short-lived and thus are not excellent sharing candidates. But, if we included zero pages, those numbers would increase somewhat. We also see that there's peak sharing up to as high as 50%. So this indicates that at some point over this week-long period, a lot of these machines had a very, very high level of internal redundancy. So that's certainly interesting. And then we also see that there's sort of a baseline level of sharing of around 8%, meaning that at any given time during this week-long period, there was always at least around 8% possible internal redundancy. So bottom line here, what we're seeing is that there is actually a significant amount of self-sharing potential that we're observing in these machines. Well, now let's look at what we can see from sharing between these various machines. So this graph here shows along the x-axis we have a variety of pairings of these various machines. We have actually, on the left here, we have the 6 pairs of machines that shared the most, and then all others are averaged on the right. And then again, along the y-axis, we have the percentage of inter-VM sharing. Now, pretty striking compared to the last graph is that sort of even in the case of these pairs of machines that were sharing the most, the average sharing we're observing here is only around 2%, so that's very, very low. In all other pairings, in this case with these 7 machines, there are 21 possible pairings. So in 15 of those 21 pairings, the amount of inter-VM sharing was effectively 0, less than 0.1%. And during this week-long period, if we considered any 2 traces from different machines, we never observed inter-VM sharing that was ever above 6%. So bottom line here is we're seeing that there was actually quite a small amount of inter-VM sharing potential we were observing in these machines. So what are sort of our high-level observations from this? Well, first we saw that there's sort of, typically we were observing about 15% possible sharing, which again is significant, but possibly less than we might expect, based on, synthetic workloads we've seen. But what's also very interesting about what we've seen is that most, on the order of 85% or more of this sharing was actually derived from self-sharing. Now, one question that is good to ask here is, well, what about co-locating many VMs? Maybe we only looked at pairs here, but as you add more VMs together, you're going to increase the amount of sharing between VMs, which is true. So we looked at, for example, co-locating all 7 of those machines. Well, when we do that, actually, still over 80% of the total sharing we see is just from self-sharing. Less than 20% is actually being contributed from sharing between those 7 machines. Another reason this result is actually quite interesting is that self-sharing doesn't actually require virtualization necessarily to capture. Although we normally think of sharing only within virtualized systems, self-sharing could also be entirely captured either within individual VMs or even further within a completely non-virtualized host system. So hopefully I've convinced you that self-sharing is significant. But of course, this raises the question, well, what is actually causing some of this self-sharing? So to get some insight into this question, we conducted a case study of self-sharing in which we looked at what causes self-sharing in a Linux desktop. And again, here we're looking at sort of non-zero sharing because that's sort of the more interesting kind of sharing. So to get some sense of this, we used an expanded version of the memory tracer we used to collect our real-world Linux traces. And what our expanded tracer does is, in addition to the contents of pages, it also, or rather, in addition just to the hash values of individual pages, we also track their contents and the processes using them. So a simple example of what this might look like, we might have a page that looks like this. This is a page of libc, and it's being used both by the SSH process and an Apache process. So what having this kind of information from a memory trace allows us to do is it basically allows us to group the sharing involvement, as a percentage of the total self-sharing, both by the content that's involved in that sharing and also the processes that are involved in that sharing. So let's look at what that looks like in the case of a Linux desktop. So first, let's look by process. So this graph here, along the x-axis, we have a number of different processes. On the y-axis, we have the percentage of sharing involvement. And we've broken this down sort of by processes that are related to GUI applications and then sort of processes that are sort of background command line processes. Now, what we're seeing here is that the highest sharing processes, those that are sort of involved in at least 30% of sharing, are basically exclusively processes relating to either GUI applications or GUI libraries. And then, system background processes are involved in significantly less sharing. Now, in this case, this is probably largely due simply to the fact that we're looking at a desktop workload here, so the memory footprint of our system is probably dominated by the GUI. So probably what this is indicating is that the self-sharing we're seeing is simply a result of the user workload we happen to be running, which in this case is a number of GUI applications and GUI libraries. So we can also look at self-sharing we see broken down by content. So this graph here shows along the x-axis we have, in red we have some individual shared libraries, and then in blue we have the total of all shared libraries, all program heaps, and all program stacks. Now what we're seeing here is that almost all of the self-sharing we're seeing is related to either shared libraries or program heaps. Now, we think that a lot of the sharing that, for example, we're seeing in all of these, this duplication we're seeing in program heaps is due to the fact that a lot of these processes are probably recreating data structures, and that's causing some internal redundancy. And sort of a good little example of how this might be happening is, in this particular example, the single most shared page in the system was a single heap page used by the X server, which had about 600 unique copies. And so that was about 2.3 megabytes of sharing from this single 4 kilobyte page. So we think this is a good indication of how what is most likely happening is that there is some duplicate data allocations going on in these processes, and that's causing a lot of this self-sharing to occur. So next I'm going to talk about some specific factors that have an impact on sharing. So here the question we're basically asking is, how do various specific properties influence sharing, and how important relatively are they? So we can consider a number of different characteristics. For example, about an operating system, we can consider, what is the family of the operating system? So, broadly speaking, is it Linux, Windows, Mac, so on and so forth. We can also consider, different versions of a given operating system family, such as, Windows XP versus Windows 7. We also can consider, different architectures. In addition to the OS itself, we can also consider, the application setup. And here again, we're looking at kind of a, server and a desktop setup, roughly emulating what you might see in sort of a LAMP setup or a VEI setup. We can also consider some factors such as the granularity of sharing. So this is again referring to how the granularity with which you break up memory when you're actually performing sharing. And then we're also kind of interested again in sort of new OS technologies. And the one I'm going to talk about here is address space layout randomization, and we'll get to that in a little bit. So first let's look at what we see in self-sharing across some of these VMs we looked at. So this graph here shows a number of our VMs we set up along the x-axis, and along the y-axis we have the absolute self-sharing we saw in each of these VMs. Now, we're seeing here that there are some fairly significant differences, just by looking at different OS families and also versions. So, for example, in this particular case, we saw, significantly higher self-sharing in our Mac VMs and our Windows XP VMs versus our, Windows 7 or Linux VMs. In contrast, we're seeing, much smaller differences between minor versions and OS architectures. So again, we're seeing, pretty significant variations here just between base OSs. But again, what's sort of more interesting is looking at what we see when we're considering sharing across virtual machines. So again here, if we have, say 10 VMs we're looking at, there are a lot of different possible pairings. So I'm going to present sort of a number of selected results that sort of demonstrate what we're seeing. So first, let's look at varying the OS family. So this graph here shows a few results looking at, for example, Mac versus Linux, Windows and Linux, and Mac and Windows, and the amount of inter-VM sharing we see between those. Well, what we're seeing here, and also, in red we have just the base system where we're not running a workload, and then again we have those server and desktop workloads. Well, what we're seeing here is that basically across OS families, there's very, very little sharing, on the order of less than 5 megabytes, so close to nothing. Well, now let's consider what if we take the OS family and rather than varying it, let's hold that fixed and instead vary the major version of the operating system. So in this case, we're looking at Windows 7 versus Windows XP. And what we're seeing here is that, as in the previous case, there's very little sharing going on in sort of the base system, that's in red. But when we add in those applications, we're actually seeing a much higher level of sharing. In this case, above maybe 50 megabytes, at least in the case of the desktop workload. So now let's try holding both the family and the major version constant, and let's just vary the minor version. So here we're looking at two different versions of Ubuntu, 10.4 versus 10.10. And here what we're seeing is that we are again seeing that fairly higher sharing in applications, but we're also starting to see some sharing going on here just in the base OS, not dependent on the applications. So what we've sort of done here is we're sort of, by fixing the major version, we're also recovering some sharing in the base operating system itself. And finally, let's consider holding everything constant except the OS architecture. So this is just looking at some variations of 32 and 64-bit versions of the same OS. And what we're seeing here is the highest levels of sharing of any of these four graphs, on the order of over 100 megabytes across architectures. So this is again sort of indicating that modifying the architecture is not actually having a particularly detrimental impact on sharing potential. So these are a lot of graphs here, but what is sort of the high-level picture we're getting from this? Well, this is sort of suggesting something of a sharing hierarchy, where starting from a heterogeneous system where you're seeing very little sharing, you're sort of gradually recovering sharing as you move along this hierarchy and are fixing, the family and then the applications and so on and so forth. And furthermore, what we're kind of seeing is that, fixing that OS family and then secondarily the applications is sort of the most important factor in achieving this sharing between VMs. And then other factors such as the version and the architecture are of somewhat lesser significance. So let's also now briefly look at sharing granularity. So normally when we're sharing memory, we're sharing on a level of 1 hash per page, but there's no restriction that we actually do that. We can also consider either higher or lower granularities. So this graph here is showing the amount of sharing we see in one example when we vary that hash size as a multiple of the page size. So one thing that we're seeing is that we're sort of only achieving decent returns when we divide pages evenly. So that would be in this graph 0.51 or 2, which kind of makes sense because OSs are allocating memory on the granularity of a single page. So obviously we'd like to evenly divide that. We're also seeing that there are sort of diminishing benefits from increasing the granularity of sharing. So for example, as you move from 1 to 2, you double your number of hashes. You do increase the amount of sharing you see, but not by quite a factor of 2x. And this graph doesn't show it, but if you sort of extend that further and look at even finer granularities, you again see sort of leveling off gains. And those kind of results have also been reported in some other work. So bottom line here is we're seeing basically that there's a trade-off between the overhead we're willing to handle in terms of number of hashes we're processing and also the sharing potential we're observing. Finally, I want to talk briefly about address space layout randomization. So this is a security technique that basically involves randomizing the location of certain parts of a process's memory space in order to foil attackers who might otherwise know where certain things are. And now, since this is a technique that actually has some direct impact on memory, it's sort of a natural question to ask, does this actually have a negative impact on memory sharing? So to get a sense of this, we looked at 4 different implementations of ASLR. In Linux, we looked at both the implementation in the mainline kernel and also sort of the improved implementation in a PAX patch kernel, which is basically a kernel used in some hardened Linux distributions. We also looked at the implementation in Windows 7 and Mac OS X. And to get a sense of their impact, we ran our desktop application workload both with and without ASLR and looked at the relative amounts of sharing between them. So what does this look like? Well, this graph here shows for each of these 4 ASLR implementations what the sharing reduction as a percentage was when we enabled ASLR. So what we saw was that in 3 of the 4 cases, we saw at least a 10% reduction. So that is certainly significant, not horrible, but certainly significant. And another interesting thing we saw was that sort of when we moved from the mainline Linux implementation to sort of the improved Linux implementation, the impact on sharing got a little bit worse. So that sort of is another good example of how we might be doing something we consider good. We're improving our security, but in this particular case, it also has a slight negative impact on our ability to share memory. So bottom line here, we're seeing that ASLR certainly doesn't prevent us from doing this memory sharing, but does reduce the potential we can get from it. So what are our observations from this study? Well, we saw that there's something of a hierarchy with respect to sharing potential, where at the top of that hierarchy is sort of the OS family and the application setup, and then below that is sort of the version and the architecture of the OS. We also saw the very important role of platform homogeneity. In particular, we saw that across heterogeneous systems, we saw very minimal sharing possible. When we looked at homogeneous systems, we saw there were significant gains in the amount of sharing possible, but still fairly modest absolute levels. We also saw how we can leverage finer grain sharing to improve sharing potential, but that's sort of, again, an issue of diminishing returns. And then we also saw how OS improvements, in particular, we looked at ASLR, may have a negative impact on sharing. So what are our high-level conclusions from this? Well, we conducted a study into some practical issues of page sharing, looking at both some real-world memory traces and also some specific sharing scenarios. In our real-world traces, we saw sharing generally around the level of 15%, which is, again, significant but less than expected. But perhaps more interesting than that is the fact that the vast majority of that sharing we saw is from self-sharing, which, again, as I said earlier, you could potentially exploit without using virtualization at all. We also studied a variety of factors impacting sharing. We saw that there's a key role of homogeneous platforms, and we also saw varying impacts of sort of modifying other various OS characteristics. And we also got, with ASLR, we sort of got a taste of how evolving technologies in our operating systems can have an impact on sharing potential, even when we might not be intending them to. Thank you, and I'll take any questions.
Hi, Fred Douglas, EMC. So you mentioned fine-grained sharing, and
yes.
I think in your case this means shrinking the page size,
yes.
right?
Yep.
But in the related work, you talked about fine-grained sharing, meaning doing deltas to find things that are similar. And I'm curious
yes.
whether you can use your data to analyze the benefits of doing the kind of difference engine approach in a real-world setting.
Yeah, so we didn't look at that specifically. I think that is sort of taking finer grain sharing sort of to the next level. I mean, if you consider, arbitrarily fine grain sharing, you're basically getting to that idea of patching where you can, capture sharing when you have pages that are quite similar but not identical. So no, we didn't look specifically at that case, but there are definitely gains to be had from doing that kind of thing.
Thomas Barr from Rice University. So you looked at small multiples of the page size, but I'm wondering if you looked at large multiples of the page size to reflect the next size up page size on x86, something like 2 megs.
We didn't look. I think there's been significantly more work looking at very fine-grained sharing rather than sort of very coarse-grained sharing. We didn't look too much more about coarse-grained sharing because in our experience, it got pretty bad pretty quickly when you considered coarse-grained sharing. So it definitely, I think, dropped off more than would be considered reasonable. I mean, obviously, all the systems we're looking at are using 4 kilobyte pages. So, if your operating system is allocating at a different level, then maybe you would see something different from that.
All right, thank you.
Arlen Congarlo from NetApp. Do you have any ideas or explanations as far as why previous published numbers on effectiveness of sharing was much higher? Is it because they were done on, synthetic workloads have smaller working sets? Or is it because they were done on freshly booted VMs with many 0 pages? Or?
Yeah, well, again, this I think gets sort of back to what was mentioned in the last talk, was that these kind of things always depend on the data. And I mean, again, what we were sort of very interested in here was sort of taking some completely uncontrolled memory data and looking at what we could see with it. So obviously, as previous work has reported, there are certainly cases where you might see much higher levels of sharing, and if you do, then great. But I think sort of what you might say the takeaway message here is that if you can can run your tests and run your experiments and see that you're going to achieve 50%, 60% savings, then great. But sort of if you don't have the numbers backing that up, then sort of proceed with caution. Maybe is one way to put it.
Thanks.
Vasily Tarasov, Stony Brook University. So, do you know about kernel same page merging in Linux kernel?
Yeah.
So was it enabled or disabled, and did it affect self-sharing with your recording?
We didn't actually look at that. So yeah, KSM is actually a good example here because that is sort of an existing technology that could potentially be used to do what we're talking about, which is basically doing sharing within the OS itself. I mean, again, when we're looking at actual live systems, it's going to largely depend on how effective they actually are. And in this work, we're obviously not looking at all at an actual implementation of a system that is capturing sharing, but rather, what is the maximum potential sharing we could possibly capture.
Right.
But yeah, looking at KSM would definitely be worthwhile.
Yeah, that would be very interesting to see if that potential that you're reporting is actually achieved by KSM or UKSM.
Yeah.
So, thank you.
Xiang Song from Shanghai Jiao Tong University, and as memory may change from time to time because the operating system is processing data. So how many data can actually benefit from memory sharing? Because there may be a lot of sharing pairs existing for a short of time, so it is not beneficial to sharing the data.
Yeah. So actually, the paper I mentioned earlier of the Satori paper looked a lot about that issue specifically, which is basically this issue of sharing data that is very short-lived. And they were reporting that there was a significant amount of that. Obviously, if you have sharing that is too short-lived, then it becomes increasingly difficult to capture. Obviously, having stable long-term sharing is the best case. But there definitely could be cases where we may have a lot of potential sharing, maybe, but are not actually able to capture it. And so that's sort of a separate issue of, you may have some amount of potential, but then obviously the next step is, well, you actually need a real system that can go in and capture all that reliably.
So maybe you can provide a CDF graph about the long time of sharing memory pairs and the amount of memory that can be shared.
Yeah. I mean, there are definitely interesting things to look at in terms of temporal changes in the amount of memory.
Okay, thank you.
Oh Yang from University of Pittsburgh. I have a question about the footprint, size of the memory footprint of your workload. Because given that the footprint of the OS itself is very small, actually much of the memory is used for page caches for I/O memories. And so I'm wondering, will that be a factor, the memory actually used by the workloads influence the amount?
Yeah, I mean, that's definitely a very important factor.
Yes.
I mean, like in our results, like again, when we were looking at that case study of Linux desktop sharing, we're seeing a lot of GUI sharing probably due to the fact that, most of our memory overhead is due to GUI applications. So obviously, very, workloads that don't use a lot of memory are obviously not going to show a lot of sharing potential. So yeah, I mean that is definitely a very important issue.
Actually, how much memory are used by the workloads? Like 2
Well, our
gigabytes?
VMs were provisioned with I think 2 gigabytes of memory each. So I mean I can't speak exactly to how much memory they were using, but I mean we were running a large number of applications, so I think it was using a substantial amount of that.
I see. Thanks.